You might not be able to tell, but I'm driving a car right now. But what is a car? And whence does it derive its power? Well, my friend, the answer is hydrocarbons. More on that later. But first, hydrocarbons. You've probably heard that carbon is the building block of life. But what does that mean? Well, carbon, along with its buddy hydrogen, and a couple of other key elements, actually form the basis of all these compounds, as well as the many fuels and plastics that we still use in society today, such as the fuels I was using to power my car earlier. So, hydrocarbons. What are they? Well, the first thing we need to understand is carbon. So carbon, this is an element we have on our periodic table, as you can see here. It has 6 protons, usually around 6 neutrons, and importantly, it's in the 4th group. This means that carbon will form 4 covalent bonds when it's bonding with any other atom. What is a covalent bond? That's just when we share electrons. For example, with hydrogen and another hydrogen, each of these hydrogens has 1 electron in its outer shell. So when these two come together, they really want 2 electrons in their outer shell. So each of them have 1, they're both going to share those 2 in the middle. So this hydrogen has 2 electrons, this hydrogen has 2 electrons. They've both shared those electrons. And that's what a covalent bond is, essentially. With carbon, we're going to do the same thing, but 4 times. Now, while we're talking about bonding, there's something else we should probably mention. Electronegativity. What's that? Well, you heard me say before, right, that hydrogen has 1 electron, but it really wants to have 2 in its outer shell. That means it really wants to bring in another electron. It's really hungry. It wants to bring it in. We say that's electronegative. In fact, the most electronegative atoms are far more electronegative than hydrogen. This occurs when they have roughly around 6 or 7 electrons out of 8 in their outer shell, so they really want to bring in 1 more to complete their outer shell, and also when they have a much smaller atomic radius, which means the electrons are closer to the nucleus, so it's easier to draw them in. Yeah, the most electronegative elements are here. Funkelbrisk. This means that the most electronegative element is fluorine, followed by oxygen, followed by nitrogen, followed by some other ones that we're not really going to need to talk about for today. What other bonds do we have within these molecules, and how do those influence the properties of the molecules? Due to electronegativity, if we have 2 atoms bonded together, but one of them really wants electrons and the other one, maybe kind of wants electrons, but not so much, then we're going to have what's called a polar bond forming. So it's still going to be a covalent bond, because this isn't the kind of ionic bond we have where one completely wants electrons and the other does not want electrons, so all the electrons get shoved over to one atom. This is where we're still sharing those electrons, but one of them is just sharing them a bit more. Now, hydrogen always has 1 electron in its outer shell, and oxygen will always have 1, 2, 3, 4, 5, 6. What hydrogen and oxygen do is they're going to share these 2 electrons. So the hydrogen now has 2 and it's happy. Oxygen has 1, 2, 3, 4, 5, 6, 7, but it wants to have 8. So it's missing 1, so we have a charge of -1. But overall, what we're going to see happening in this bond is, since oxygen, as we said before, is one of the 3 most electronegative elements, this electron, or these 2 electrons, are going to spend more time over near the oxygen side of the bond, which means this part is actually going to have a partial negative charge, which we write as this, because more electrons means it's a more negative charge, whereas the hydrogen will have less electrons spending time over here, so it's going to have a partially positive charge. Okay? This forms what we would traditionally call a polar bond, or even a dipole, which just means we have a separation of charge. Now also, intermolecular forces. What are those? So we've talked about intramolecular forces. That's like a polarity in molecules, where one of the atoms hogs the electrons more than another atom. But what are intermolecular forces, I hear you cry? Well, intermolecular is when we have a force between 2 different molecules. So for example, if I have a hydrocarbon chain that looks like this, I'm going to be talking lots about hydrocarbon chains like this, but just as a brief example, this has 4 carbons, 10 hydrogens, and this is called butane. When we're talking about intermolecular forces, we're talking about which forces are actually going to be drawing these 2 compounds together. So what's going to hold, if we have a whole, 6 times 10 to the 23 of these little molecules, that'd be 1 mole, what is going to hold those molecules together and stop them from just flying apart? And that would be the intermolecular forces. So the weakest kind of intermolecular forces that we have are called dispersion forces. What are those? Well, let's consider what we have. For this butane, we're going to have electrons. This is probably way too many, but just so you get the general idea, we're going to have some electrons floating around. We're going to have the same thing with this butane. And what we're going to have happen, sometimes the electrons are going to be spending more time over here, sometimes they'll spend more time over here, whatever. So if we have electrons that, some of them just spending a little bit more time over here, which is going to happen because they're just moving around randomly pretty well, then what we're going to have is this side of the molecule is going to build up a negative charge. And because of that, what do we know about negative charges? They repel negative charges and they attract positive charges. So in this case, we're going to repel these electrons. Maybe they'll go back here. And it won't be super drastic. I'm just drawing this out so you can get more of an idea of it. But now we have more electrons here and less here. So this is going to build up more of a positive charge. And then what do we know about negative and positive charges? They attract. This is what we've got here. The positive and the negative attract. So this is just because of the random movement of electrons. It induces a temporary dipole, such as what we have here, and that's going to draw these molecules together. Now, because these are only temporary and they're random, these dispersion forces are quite weak, and they are in fact the weakest of the three intermolecular forces. What would increase our dispersion forces naturally is if we had more electrons, because then we're going to be able to build up a stronger negative charge here, or a stronger positive charge here, or whatever. And we're going to have more electrons if we have more atoms, which generally means we're going to have a higher molar mass of the molecule. So if we have a higher molar mass, we have higher dispersion. The other thing is we need to make sure we have molecular shapes that are actually going to be able to pack nicely with each other. So if I have a more chunky molecule, such as this, and again note that we're making sure that carbon has 4 covalent bonds in each of these examples, because that is what we worked out it should have before. If I have 2 of these molecules trying to get close to each other, that's really not going to happen as favourably, because instead of having like 4 carbons or 3 carbons in a row as we had before, we're only going to be really having, and I'm going to ignore the hydrogens here just so you can get the general picture, and also because I don't really have room, we're only going to be able to really get these 2 bits close, which is going to form much weaker intermolecular forces. So we also want to have favourable molecular geometry. So those are the 2 things: molar mass and molecular shape, molecular geometry. These shapes will not be able to pack as nicely, and so they're going to have weaker dispersion forces. Now, the next type of intermolecular force is a dipole-dipole force. If we had 2 of these alcohols, remember we earlier said that when we have oxygen bonded to hydrogen, since oxygen is more electronegative, this will build up a negative charge. This one builds up a positive charge. Same thing over here. What we're actually going to have is, like before, where we had a negative attracting a positive with a temporary dipole. This is a permanent dipole. There will always be more electrons near the oxygen. So these forces are going to be stronger, and the negative will attract the positive. The negative will attract the positive, and they'll be drawn in strong. And because this is because of the 2 permanent dipoles, they're attracting each other, we call these dipole-dipole forces. These are much stronger, as we said. Another example of a dipole-dipole force, if we have carbon and oxygen, carbon, this isn't a compound that actually exists. I'm obscuring a lot more of what's happening, but just for the sake of seeing these 2 forces, Funkel-Brisk, oxygen is still more electronegative than carbon. They have a positive charge build up at the carbon and a negative charge at the oxygen. Positive and a negative will attract each other. So again, these 2 permanent dipoles are causing the 2 molecules to be attracted to each other more strongly. Now, the third type of intermolecular force, I've actually already given it away, accidentally. This third type of intermolecular force is just a stronger form of dipole-dipole. So if you remember Funkel-Brisk, the most electronegative elements are fluorine, oxygen, and nitrogen. Hydrogen is not very electronegative. So if we have one of fluorine, oxygen, or nitrogen
bonded to a hydrogen, that is going to build a stronger dipole. These elements are going to steal the electrons much more, and the hydrogen will be left as a single lone proton, far without its electron and just a positive charge. And since it's simply just a single lone proton, this allows us to form some really strong dipoles between these hydrogen compounds, and that's actually what we've got going on here. So the hydrogen is just a lone proton, and the oxygen is really pulling in these electrons. And we call this hydrogen bonding. Hydrogen bonding occurs when we have hydrogen bonded to one of these top three most electronegative elements, and that's going to create such a strong dipole that's going to create really strong intermolecular forces. So in summary, we have dispersion forces, which increase with molar mass. We have dipole-dipole, which is stronger than dispersion, and it's because of permanent dipoles. And we have hydrogen bonding, which is the strongest of all of these. It's actually just a subset of dipole-dipole, but a very strong subset, so strong that we give it its own name. So what happens with these stronger intermolecular forces? Let's talk about dispersion forces. So with, for example, a hydrocarbon molecule, as we saw before, they don't have any permanent dipoles that are going to be forming, because all we have is carbons and hydrogens. And because of the geometry of a molecule such as this, even with hydrogen maybe being slightly more electronegative, really not, but slightly more electronegative than carbon, even if this draws some electrons over here, the other hydrogen on the other side is going to cancel it out and draw them right back. So overall, there's going to be no net movement of electrons, and there'll be no permanent dipoles forming. Thus, the only force between these hydrocarbon chains, which we'll call alkanes, alkenes, and alkynes, the only force between these is just going to be dispersion forces. As such, if we have like a vial of these hydrocarbons, they're just going to have some weak forces pulling them together, and it won't take much energy to get these molecules to separate and expand and turn from a solid to being a liquid or to being a gas. We can see this in the boiling points of the alkanes, alkenes, and alkynes. The boiling points are quite low because it doesn't take much energy to break apart those bonds and to pull them apart and to get them to boil, to get them to form a gas. And we'll see this in the graph that we look at later on, and also as we discuss practical applications of hydrocarbons. Since the intermolecular forces are so weak and the boiling points are so low, we have to store them in careful containers because they're so volatile. They would easily explode if we accidentally gave them enough heat energy to do so. So we have to be really careful with those. Whereas, if we have dipole-dipole forces, because these are stronger, they're a permanent dipole, they're actually going to take more energy to separate, and so the boiling point of these will be higher. And this same trend continues into the hydrogen bonds. So since hydrogen bonds are so much stronger, it's going to take a lot more energy to break them apart and to get them to boil or to melt. So the melting point and the boiling point will increase. What about the solubility in water? That's the next thing that I've been prescribed by the chemistry gods to talk about. So if we have water, as you can hear around me pretty well, it kind of holds together in chunks. If I get a lot of these water molecules together, water is just H2O, as we know. Oxygen is more electronegative, so we're going to have a negative charge forming on the oxygens and a positive charge forming on the hydrogens. And because of hydrogen bonding, which is just a specific form of dipole forces, we're going to have these compounds pull each other together. Positive attracts negative. These compounds will pull each other together. And so we have all these water molecules that are kind of just clicking together. And if I have a molecule such as this little alcohol here, since it has 3 carbons and it has the functional group of the OH, which is called hydroxyl, it has that on the first carbon. We're going to call this 1-propanol. We're going to have the partial negative charge build up on the oxygen, partial positive on the hydrogen, because oxygen is more electronegative. And then we have water molecules. Let me draw another one of them water boys. Come over here. Let's talk about the types of forces in these, in the hydrocarbons. Between if I had more alcohols up here, pulling those together, we have the hydrogen bonds and a little bit of dispersion forces. Those are going to be our cohesive forces because they're between like molecules. And here I have cohesion forces between the hydrogens, these forces of attraction. But if I try to break apart those cohesive forces and form adhesive forces, which are between two different molecules, so the water and the propanol, one propanol, then we're going to need probably some kind of similar bond. And luckily for us, we have hydrogen bonding occurring in both the alcohols and the water, so we're going to be able to break apart these bonds if we happen to get a water over here, which is fairly likely because it's like a quarter of the molecule. Is going to break apart the cohesive bonds and form adhesive bonds so that the alcohol can dissolve. And that is what we find. We find that these smaller alcohols and things, those are going to be quite soluble. But if I were to increase the length of this chain, let's add a lot more carbons. And you know there's going to be hydrogens there. There's 3 hydrogens, 2 hydrogens, 2 hydrogens, da-da-da-da-da. I don't need to draw them. You know what we're going to have. If I have some water molecules floating around, it is much less likely that it's actually going to go over near the hydrogen bonding, and there's more chance of it just going over where there's dispersion forces between the like molecules of this long alcohol, which means it's going to be less likely to break apart the cohesive bonds and form some bonds between the water molecules and the alcohol, which is what we would need to do to dissolve it. So that means as we increase the length of this chain, the solubility is actually decreased, because it's going to be harder to get the compounds to dissolve in water. And that's all because of this rule that like dissolves like. We need a polar bond to break apart a polar bond. And if we were going to dissolve something with completely non-polar bonds, like the alkanes, alkenes, and alkynes, we would need more alkanes, or maybe a different type, because those are both non-polar, and the dispersion forces can break apart other dispersion forces to form new dispersion forces. So polar dissolves polar, and non-polar dissolves non-polar. And always remember that as we increase the length of the chain, as we're dissolving in water anyway, we're going to increase the solubility. We've talked about intermolecular and intramolecular forces of these compounds. We've talked about the mechanisms for their solubility and for their boiling point, but what we haven't talked about is what it actually consists of for the individual compounds. If we take a single homologous series, which is basically a family of different compounds with all the same functional group, let's take a look at, for example, the alkanes. So the simplest alkane is methane, which has 1 carbon and 4 hydrogens. And then we have ethane, propane, butane, pentane, hexane, octane, etc. What I was doing there was just increasing the number of carbons, but it's still a fully saturated hydrocarbon chain. Now, as we increase the number of carbons, what we're doing, as I said, if we increase the molar mass, we're going to increase the amount of dispersion forces. And adding carbons, and also hydrogens with them, is going to increase the molar mass. So going further up a homologous series, by adding more carbons, is going to increase the amount of dispersion forces. Okay? And what we're going to see because of that is that if we have methane all the way up to like octane on a graph, the boiling point here is going to be fairly low, and then as we go up, the boiling point is going to rise, because more dispersion forces means it will take more heat energy to break apart those bonds, so the boiling point will rise. And remember, the boiling point is basically just an indicator of how strong the forces between the molecules are. Even though it actually physically represents something, it's nice to think of it as just a simple indicator. Now I'm supposed to talk about within all the other homologous series, such as alcohols, aldehydes and ketones, organic acids such as carboxylic acids, or bases such as amines, and also we have the amides. But the trends for all of those are basically pretty much the same. As we increase the number of carbons, we're still keeping the same functional group, so the main bonds, whether it be hydrogen bonding or dipole-dipole, those will be the same, and we're just going to increase the dispersion forces in the chain. So we've got our functional group, we add more carbons, and we'll have more dispersion forces, which are going to create more intermolecular forces between the molecules and increase the boiling point. The only exception to this is the amides. As we'll talk about later, the amides actually form a complex network of hydrogen bonds between all the different molecules. It's not as simple as we have one single functional group and then it attracts another functional group, and then we're adding carbons to the carbon chain, so the dispersion forces will increase. The more complex networks means that it's a more complicated trend in boiling point. In fact, amides have a fairly high boiling point, as we'll talk about, but as we increase the number of carbons, that boiling point stays roughly the same. Like, it changes a little bit, but it's not a major clear rising trend. It's still around the same boiling point. So those physical properties, such as boiling point, which increases as we add carbons, or solubility, which generally tends to decrease as we add carbons, because the long hydrocarbon chain will outweigh the polar head or whatever we have. Those are our physical properties within each homologous series. But what about between these homologous series? which homologous series or which family of compounds tends to have a higher boiling point, which tends to have a lower boiling point. So that's what we're going to talk about now. Let's start off with alkanes, alkenes, and alkynes. Those generally tend to have the lowest boiling point. Why? As we talked about before, dispersion forces are weaker than dipole-dipole and hydrogen bonds, and since alkanes, alkenes, and alkynes can only form dispersion forces, those are going to have weaker intermolecular forces and thus have lower boiling points and lower melting points. Okay, now there's one thing I neglected to mention for the alkanes, and that is that there's a bit of an anomaly in the melting points of those, and that is due to, as we talked about before, dispersion forces are impacted by two main features. It's the molar mass, obviously increasing carbons overall will increase the dispersion forces and thus the melting point, and they also need to be able to pack well, which at the time we said was just because of the molecular geometry. We can see that in this trend, the melting point, methane, then ethane it actually decreases, propane decreases again, and then after propane it starts to increase. So obviously as the melting point is increasing, because of the increased number of carbons, that's due to the increase in molar mass and thus stronger dispersion forces, so it will take more energy to break it apart. However, what's causing it to dip down? Well, if we follow that trend backwards, going from propane, then to ethane, then to methane, we're going to see the melting point will rise. And that is because as we get these smaller molecules, they're actually able to pack in better with other smaller molecules. Pack. They're packing in closer, the strength of their dispersion forces will increase, and thus the melting point will be higher. And as we, from methane to ethane to propane, as we increase the number of carbons, we're going to make the chain longer, so as it's longer, it will pack slightly worse, weaker dispersion forces, and the melting point dips to the actual lowest alkane melting point is propane. After that, we're going to see the melting point continue to rise as the effect of molar mass continues to take over. Now, what about the physical properties between these homologous series? So here on the screen, you can see the overall main order. We go alkenes, then alkanes, then alkynes. That is in order of increasing boiling point, which, as we said, means an increase in strength of intermolecular forces. And as we continue, we will then have amines, and then amines, and then aldehydes and ketones, then alcohols, then carboxylic acids, and then amines. So that is in order of increasing boiling point. Let's talk about why that is, and it's going to help us as we go in to look at our graph later on. So hydrocarbons, alkenes, alkanes, and alkynes, these have the weakest intermolecular forces because they only have dispersion forces acting between them. We actually have a slight thing coming into play because of the molecular geometry. So as we can see from these pictures on the screen, if we have carbon forming one double bond with another carbon, that forms a tetrahedral geometry. If we have it forming two double bonds, that forms a planar geometry. And if we have it forming three double bonds with an adjacent carbon, that forms a linear geometry. And now, the linear geometry of alkynes actually means that they are able to pack slightly more efficiently than alkanes and alkenes. So alkynes have the highest boiling point out of the hydrocarbons. So then we just have to decide between the alkanes and the alkenes, which of these has the highest boiling point. And instead of talking about molecular geometry here, we just talk about the dispersion forces. So alkanes have two more hydrogens than an alkene, which means they have a slightly higher molar mass and their dispersion forces are stronger. Thus, alkanes will have a higher boiling point than alkenes. So we go alkenes, alkanes, then alkynes within a hydrocarbon. Okay, let's talk about one of the organic bases because it comes up. We don't need to go into why this is a base, but it's fairly simple. So if we have an R, and this R here basically stands for the rest of the carbon chain that we know is there, but we don't really need to talk about it. Here's another R, let's signify it's different with a dash. Nitrogen has a lone pair of electrons here. And we actually have hydrogen bonding going on here. But remember, Fonkel-Brisk, nitrogen is the least electronegative of the three atoms that can undergo hydrogen bonding. So this is going to be some kind of weak hydrogen bonding. Still hydrogen bonding, so it's stronger than the dispersion forces. But the nitrogen will draw away electron density from the hydrogen. And that will allow in the formation of a single attractive intermolecular force between this partial negative and this partial positive charge. Okay? Now that's going to draw these two together. They're going to attract. And we have hydrogen bonds in nitrogen. We only have one. So this is going to be pretty weak. Still stronger than alkanes, alkenes, and alkynes. And that'll mean that these amines have a higher boiling point than hydrocarbons. But they still have a lower boiling point than the rest of the atoms that we're going to talk about. The compound with the next weakest intermolecular forces are the aldehydes and ketones. So as we can see, we've got one here. This is when we have a hydrocarbon chain with the C's and the H's, all carbons still forming 4 covalent bonds, and we just have a double bond to an oxygen attached somewhere. If it's on the end, there's an aldehyde. If it's on the middle of the chain, then it's going to be called a ketone. But these compounds are still very similar. They have a similar boiling point, and that's because the only intermolecular force is the dipole-dipole forces. The oxygen is more electronegative. We actually talked about this before when we were talking about dipole-dipole forces. So here we have ethanal, and what makes this aldehyde an aldehyde is that we have one carbon that's double bonded to an oxygen. Oxygen is more electronegative. This oxygen is actually going to draw some electron density away from the hydrogen. Not directly, I suppose, but indirectly. So this will have a slight positive charge, this will have a slight positive charge. And then we're going to have dipole-dipole forces between the oxygen and the hydrogen. So negative charges and positive charges attract. And thus we've got some dipole-dipole forces forming. Now dipole-dipole forces, they're stronger than dispersion forces, which is the reason why aldehydes have a higher boiling point than alkenes and whatever we have than the hydrocarbons, but they're still much weaker than hydrogen bonds, which occur in most of the rest of the compounds. Also, I think that because we have 2 dipole-dipole bonds, that is stronger than the HN dipole bond that we saw in the amines. What's next? Everybody's favourite, the alcohols. If I have a carbon chain, I don't know why I've drawn this extra carbon here, but I guess just so you can see what it's like on the end of the carbon chain. We're going to have this oxygen drawing away electrons, same deal as always, and that means we're going to be able to form some hydrogen bonds between this oxygen, which is negative, and this hydrogen, which is positive. These are going to form some strong intermolecular forces and mean that hydrogens are going to have a higher boiling point than the amines, because oxygen is more electronegative than nitrogen, and also than the hydrocarbons because of the formation of hydrogen bonds, which are stronger than dispersion. So alcohol, the boiling point goes up further. Okay. Now what's next? Of course, it's everybody's favourite, the organic acid. Everybody loves some acid jazz. We have carboxylic acids, R to C. These are characterized by both forming a double bond with oxygen and going to this hydroxyl group like we saw in the alcohols. So we've got the same functional group as the aldehydes and as the alcohols, kind of just put into one. Let me draw this a little bit higher. Now, again, I don't need to tell you what is going to happen with these oxygens, do I? They're going to draw away the electron density, and that's going to result in the formation of, you guessed it, some hydrogen bonds between the H and the O and the H and the O. Now we actually have, this does count as a hydrogen bond because the hydrogen has its electrons drawn away from it by one of the 3 most electronegative elements, and then it's going to bond to another electronegative element. And these hydrogen bonds, we actually really have 2 of them. They're much stronger, and they're going to result in a much higher boiling point for carboxylic acids, because we have 2 strong hydrogen bonds forming. They're stronger than dipole-dipole, they're stronger than dispersion, they're stronger than just one hydrogen bond that's with nitrogen. So these are going to mean that carboxylic acids also have a higher boiling point. Again, as we increase the length of this carbon chain that we have back here, that will not affect this main hydrogen bonding that's happening. It'll just increase a little bit of dispersion forces, which will slightly increase the boiling point. Lastly, we have the amides. The amides are probably my favourite intermolecular force to talk about. Now, I've basically had to draw 4 amides here so we can get the full picture. The functional group of an amide is when we have one carbon that is attached to, both double bonded to an oxygen and to a nitrogen, which is also bonded to 2 other hydrogens. So it's the same as a carboxylic acid, except instead of OH, we have NH2. Or sometimes we could have another one of those H's replaced with some more carbon chain. But let's not talk about that right now. So for these amides, I'm not even going to draw the partials because it would take too much time. But we know that oxygen is going to draw away electron density. You're probably getting sick of me saying it by now. The nitrogen is also going to draw away electron density, not as strongly as oxygen, but still a fair bit. I haven't drawn this diagram super well, but hopefully you can still see what's going to happen. The oxygen is negative, hydrogen is positive, forms hydrogen bonds. Same over here. The oxygen is negative, the hydrogen is positive, this forms hydrogen bonds. And we're actually going to have that happening over here as well. The traditional way we draw hydrogen bonds would actually be more like this, with dots. So if you're doing a diagram in a test, do it like that. These will also bond over here. So as you can see, just this one amide has still got a complex network of 1, 2, at least 3. There might be another one off to the side here. We've got many hydrogen bonds forming around this one amide. Some of them are a bit weaker, some of them are a bit stronger because of oxygen. The oxygen-hydrogen bonds are stronger, remember, because oxygen will draw away more electrons and create more difference in charge, which attracts. So that means that amides are going to have a substantially higher boiling point than any of the other compounds, even carboxylic acids. Now, if I was to turn one of these amides into a second degree amide, which means that our nitrogen will be bonded to 2 carbons, one here and one in this chain, then even a third degree amide, then this is actually not going to be able to form hydrogen bonds anymore, because we're just going to have C's and H's in here. So we'll still have the oxygen, but the intermolecular forces will be weaker. So third degree amides are much weaker than first degree amides, and second degree amides are the same. Okay, so the next thing we have to do is, using what we've previously deduced about alkanes, alkenes, alkynes, and everything from there about the different boiling points and different intermolecular forces, is to analyze this graph and also the next one. And we have to analyze these, ignore my ridiculously large shadow, with respect to the boiling points and why they're increasing and the trends. What overall trends do we have here? If we look in this graph and in the table, we can see that it increases as we go down this list between the homologous series. So 2,2-dimethyl alkane, we have an alkane, but we have these methyl substituents on the side, which are going to prevent the carbons from getting very close, and they're going to weaken the dispersion forces. Thus we have the lowest boiling point with these. However, as we said, and this is a general trend with all of these compounds, as we increase the number of carbons, that's going to increase our overall dispersion forces. If we had a small obstructed compound compared to a big obstructed compound, we're still going to have more dispersion forces between here, even if they will be weaker dispersion forces than all the other compounds. With 2,2-dimethyl alkane, we have a methyl on this side and on this side. With just 2-methyl alkane, we only have one methyl, which means in between two average compounds, we're only going to have one methyl group obstructing them, and the dispersion forces will be stronger because there's more effective surface area that's getting closer. 2-methyl alkene, 3-methyl alkane are basically the same. We still have that one obstructing that's slightly decreasing the dispersion forces, but otherwise we only have dispersion forces, so the intermolecular forces are still going to be fairly weak. As we increase to 1 alkene and alkane, we're actually going to have the carbons can get slightly closer because we don't have any methyl groups obstructing, we just have these more straight carbon chains, and the surface area is increased, thus increasing the dispersion forces and the boiling point. As we move to alkyne, we don't even have the tetrahedral shape of the alkanes, we have a linear shape, which means they can get much closer and they're going to pack much better, increasing the dispersion forces and boiling point. The boiling point continues to increase as we move up to 2-alkanol. That is because of the presence of electronegative oxygen and a hydrogen, which forms a permanent dipole, which can thus attract another permanent dipole of the hydroxyl group on the other compound, which will create some strong hydrogen bonding forces, which are the strongest intermolecular force, as we know, which will mean it has a much higher boiling point. And we can see as we move from the hydrocarbons of dispersion to the alkanols, which have dispersion and hydrogen bonding, the boiling point jumps up significantly. The boiling point increases as we move up to 1-alkanol, because 1-alkanol, we have a hydrogen bond on the end, and we have a hydrogen bond on the end. So instead of just having hydrogen bonds on the side, which we can form much stronger bonds if we have our hydrogen bonds on the side, because our chains are attracting with dispersion forces as they pack like this, and with hydrogen bonds horizontally as they pack like this, which is going to overall increase our intermolecular forces and the boiling point. But also we still have the dispersion forces between these carbons at the ends here. which means that as we increase the number of carbons, we're still going to slightly increase those dispersion forces. It's not nearly as drastic as the jump to hydrogen bonding, but it's still going to increase slightly as we increase the number of carbons. Finally, as we move to alkanoic acid, we're going to have the highest boiling point of all, and that's because if we look at alkanoic acid, or any general carboxylic acid, because the carboxylic functional group has double bonded to an oxygen and an oxygen hydrogen, we can form two hydrogen bonds between adjacent compounds, one here between the electronegative oxygen and the hydrogen, and one here, which is going to increase our boiling point, and we can actually form a whole network of these things. We also have the dispersion forces, but mainly it's these strong hydrogen bonds that means this has such a higher boiling point. And thus, alkanoic acid sits above all the rest of them. Again, as we increase the carbons, we're going to increase the effective surface area and thus increase the dispersion forces. Okay, so here I've already drawn out the reaction pathways free of charge, and hopefully we can see them. So I've used yellow arrows to represent halogenation, pink to represent oxidation, blue to represent hydration, and the rest of them we can explain when we get to them. So we have the families that we've actually been discussing. Alkanes, alkenes, we have alkynes but they're not on here. Glucose, which is not something we've discussed, but we can talk about it briefly. We have haloalkanes, which is when we have an alkane and we substitute one of the H's with a halogen, like chlorine, bromine, iodine, whatever. We also have alcohols, which have that OH functional group we were talking about. We have esters, which we're going to ignore because they're not in this video, I don't think. We have carboxylic acids, or alkanoic acids, and we have amides. We also have the aldehydes and the ketones, which can be produced by oxidation of alcohols, and amines fit in here somewhere. I'm not exactly sure where. Anyway, let's get to it. Alkanes, alkenes, and alkynes on the top. And we can always go from an alkyne to an alkene by adding H2. Very briefly, we've got the rest of the hydrocarbon chain in these R's. We're just talking about these two C's where the single, double, or triple bond is. Well, obviously, if it's a single bond, it'll be in the rest of the hydrocarbon chain. If we have one bond, it's an alkane. If we have a double bond, alkene. If we have a triple bond, it's an alkyne. Now, with an alkyne, there are no more hydrogens on the carbons. But what we can actually do is add hydrogen. Now, these are very electrophilic. These are greedy. These want to eat up these electrons. And there are electrons that are very loosely held in this bond. So, this double bond represents 2 electrons, same as this one. Sorry, that single bond represents 2 electrons, same as this one. So if I erase that single bond, where are the 2 electrons going to go? We know that hydrogen already has 1 electron. Here's the electron hydrogen already has, and it's a bit smudged, but you can still see it. The other electron is here and here, from when we broke apart that double bond, and we're going to turn that into... from when we broke apart that single bond, and we're going to turn that into a bond with the hydrogens. So now we have turned 2 electrons in this bond and 2 electrons in this bond into 2 electrons here and 2 electrons here. We have hydrogenated the alkyne to form an alkene. The carbons still have 4 bonds, but they are now bonded to hydrogen instead of each other. We can do the same thing, and another hydrogen comes along here. If we have 2 hydrogens and the carbon-carbon double bond, this carbon-carbon double bond contains 2 electrons, so if we break that apart and put them here, and if we break the bond between the 2 hydrogens, we put the electrons here, we can now form more carbon to hydrogen bonds, and you can see this is now an alkane, because it's completely saturated. It has the maximum amount of hydrogens that it can. There's no double or triple bonds. Now, because we have to break apart the bonds between the hydrogen and the bonds between the carbon bonds are not quite as strong, but the hydrogen bonds are fairly strong, so we're going to need a metal catalyst for this reaction, which is called hydrogenation. It is a form of addition reaction. The expected product of hydrogenation, if we do it to an alkyne, we'll get an alkene, and if we do it to an alkene, we'll get an alkane. Now, for the rest of the purposes of this video, we're going to continue to talk about the alkenes, but those are quite useful in their reactive hydrocarbons. We know already that with this we can do hydrogenation, which is what we talk about here. We hydrogenate an alkyne to an alkene, we hydrogenate an alkene to an alkane. But what else can we do with these alkenes? Well, we can perform halogenation, hydrohalogenation, or hydration, which we'll get to later. or hydration. So as for hydrohalogenation, it's basically exactly what it sounds like. Instead of having hydrogen bonded to itself, we have hydrogen bonded to a halogen. And in a similar mechanism, we break apart the bonds and we turn them into bonds from carbon into the hydrogen and the halogen. We can basically react this with any halogen, so X is chlorine, bromine, iodine, whatever you want. And because this hydrogen to halogen bond is weaker, we actually don't need a catalyst with this. What else can we do to this hydrogen bond? Instead of hydrohalogenating it, and instead of hydrogenating it, we can also just straight halogenate it. Now this is where these bonds get broken, and we're going to form two halogen bonds to the carbons, such as like this. This also doesn't need a catalyst because the halogen-halogen bond is not so strong, and we can react this with bromine and chlorine. Bromine is typically more reactive than chlorine. The expected product of halogenation or hydrohalogenation would just be a haloalkane. The last example is hydration, which is where we take a hydrogen, oxygen, hydrogen. This is known as water, but if we write it like this, then it kind of looks like some of those things we had before. We have one bond between these two, one bond here. Break these apart. And oh no, we've just formed an alcohol. So one of the hydrogens goes to this carbon, and the hydroxyl group goes to this carbon. And if we hydrate an alkene, we'll get an alcohol. You'll see later that we can also dehydrate an alcohol to get back to an alkene. Now, because we need to break apart this bond here in water, we know this bond is much stronger, and we're going to need some kind of catalyst. For this reaction, we need an aqueous acid catalyst, such as H2SO4 aqueous. And it needs to be dilute. Okay, let's have an example of each of those reactions. Here is an example of a reaction from an alkene to an alkane by hydrogenation. We've got the metal catalyst in the middle. This reaction takes us from propene. We don't need to specify where the double bond is because it can only be in the first position. This is from propene to propane, okay? For this reaction, we have propene, we're adding HCl, and we're going to form 1-chloropropane. There's no catalyst needed. We formed an alkane, and it has a halogen on the first, that's the substituent, 1-chloropropane. Now for halogenation, if I take 2 chlorines and add them to propene, we're going to get 1,2-dichloropropane. This again needs no catalyst, and we've got the expected product of a haloalkane produced by halogenating an alkene. If we were to hydrate propene with the catalyst of dilute H2SO4, which is our dilute aqueous acid, we could also use H3PO4, we're going to get an alcohol. Here I've drawn propan-1-ol, but we could also have propan-2-ol if the hydroxyl group was on the middle carbon. Caleb, you need to add states to the previous reaction. Add states, text editor, whatever, I don't care. I'm pretty sure I missed that we need states. Now we're going to talk about what we could react to an alkene. If we take an alkene by a halogenation of some form, we can form a haloalkane. And how are we going to do that? Well, this hydrocarbon is actually quite happy to have all its hydrogens. It's saturated, so it's going to take a lot more energy to break apart these bonds to a hydrogen and get rid of them. But what we can do, if we take, for example, Br2, would be a liquid at this state, and butane, I believe, would be a gas. What we're actually going to be able to do, if we add in some UV light, which is the strong catalyst that we need, it adds sufficient energy for us to be able to proceed with this reaction, we actually can swap, for example, this hydrogen and this bromide. So we're going to form, and because it takes so much energy, traditionally I think only one of these can go in at a time. So we'll have C, C, C. We're going to put the bromine in here, because we've now substituted it in by substituting this H out for a Br. By substitution, we have created a haloalkane. This would be butane, and this is now 1-bromobutane, and then we just have hydrobromic acid left over. This is probably going to be aqueous, and this, I believe, would be gaseous. And alkanes are going to be the traditional families that will undergo these reactions. Let's say we have to distinguish between some saturated and unsaturated hydrocarbons. How are we going to do that? Well, remember what each of these looks like. Saturated hydrocarbons is a hydrocarbon with the maximum number of hydrogens. So if we just look at the middle of the chain, it'll look like this. But really, it's just going to be CH2, 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 all the way along. And if we have some unsaturated hydrocarbons, that means the way that these two middle carbons are bonded together is either with a double or a triple bond. And we can still do the same thing either way. But I'm just going to pretend we have a double bond. This forms an alkane, and this forms an alkene. How are we going to distinguish between these? Well, let's use our reactions that we had before. So we know that what's the reaction that we can do to alkenes that we cannot do to alkanes? This would be the addition of halogens. Specifically, if I tried to add some bromine, and this is a very common test, this is called the bromine water test. So if I try to add this to this compound, it's not going to react, unless we have a lot of UV light and we try to substitute it in. So we're going to assume that we're carrying out this test with no UV light. Whereas with this one, remember this second bond is a lot weaker than the first bond, which means it can easily break open and form bonds to these two bromines. And now this would be a saturated haloalkane. So we can only carry out the reaction with an alkene. What this means is, if we wanted to test between a saturated and unsaturated hydrocarbon, all we'd need to do is add some bromine water and see if the color change occurs. If this color change does occur, then we will go from the deep red color of the bromine to a more colorless mixture. And if we see this, this means we have an unsaturated hydrocarbon. Okay? Specifically in the chemical lab, you could get a test tube of your unknown hydrocarbon, and then you could pour in a couple drops of some bromine water. We need to make sure that this bromine water is not in excess, otherwise we'll still have some of the deep red left over and we won't be able to tell. Okay? Now for combustion, this is not something that I had on my chart, but this is something that alcohols, alkenes, alkanes, alkynes, and possibly other compounds, I'm not sure, but all of those can undergo this reaction. And what this is, it's actually not very useful to see in structural form, so let's just count up. We have 4 carbons here, and then we have 4, 8, 9, 10. So this is butane. If we add oxygen, that is what we have for combustion. And we're going to produce, always we're going to produce H2O, which is liquid. And we're going to have, there's a couple different products that we could have here. So if we have complete combustion, which is when we have sufficient oxygen, then we're going to form CO2, which is a gas. But if we have incomplete combustion, we could form carbon monoxide, or we could form soot, which is carbon, which is solid. And just for the purposes of this reaction, I'm going to pretend we have complete combustion. But we could have any mixture of these two as well if the combustion is incomplete. Now I'm just going to balance this real quick. Okay, this is a balanced equation for the combustion of butane. This reaction is actually quite important for the usages of hydrocarbons, because it produces quite a fair amount of heat, particularly for complete combustion. That will produce the most heat. And that heat is what we can use to convert into energy. And that is why we mine up so much coal, because we can combust it and produce energy. Obviously this produces CO2, which is toxic for the environment, and that causes lots of global warming, but we'll get into that later. Okay? What other reactions can we do? Well, let's continue to talk about alcohols. As you remember, we had the dehydration reaction before, where we added H and OH to an alkene over the double bond, and that produced an alcohol. What we can actually do is reverse that reaction. So we hydrated alkenes with a dilute acid to get to alcohols. We can also dehydrate them with a concentrated acid to get back to alkenes. I can still talk over it. And that's exactly what we've got going on here. So we have 2-butanol. If we react that with a concentrated acid, such as sulfuric or phosphoric acid, then we can go back to having an alkene. Removing the OH and H means we have 2 electrons that need to go into a double bond, and then water is produced as well due to the reaction between the hydrogen and the hydroxide. So that's why it's called dehydration, because we're producing water and we're dehydrating the alcohol. And speaking of alcohols, what else can we do with alcohols? Well, I'm so glad you asked. And we're about. Okay, so this is the hydration of alcohols. Next up we have oxidation. Now, oxidation is a fairly complicated mechanism, But for our purposes here, we don't really need to talk about much that's too complicated. We can just talk about what it's happening to. So oxidation, in the sense that we mean it here, only really occurs to alcohols. And as we know, we have three types of alcohols. We have primary, we have secondary, and we have tertiary alcohols. Primary alcohols is when this OH functional group is on the end carbon. If I had a secondary alcohol, that means that the carbon that the hydroxyl group is bonded to is attached to two other carbons, whereas with the primary, it's only attached to one other carbon. If I had something like this would be a tertiary alcohol, because the hydroxyl group is bonded to a carbon, and that carbon is bonded to three other carbons, okay? Three other carbons means it's a tertiary alcohol. Now, oxidation, really it means that we're increasing the oxidation state of this carbon that's bonded to the hydroxyl group. But again, for our purposes, we can think of that more simply as the carbon is forming more bonds to oxygen. So in this case, we only have carbon bonded to one oxygen. But as we carry out the oxidation, for a primary alcohol, the first step is to increase the bonds to oxygen by making a double bond to this O. Because remember, oxygen always needs to form two bonds. Here it's got one with the hydrogen, one with the carbon. Here it has two with the carbon. And then the other hydrogen fills out carbon's four bonds. So this is an aldehyde. So the first step of oxidizing a primary alcohol produces an aldehyde. But these aldehydes are very reactive. So this will almost immediately react to form, that's right, our old friend, the carboxylic acid. So here we can see carbon has formed one bond to an oxygen. Here carbon has formed two bonds to an oxygen. And here, carbon has formed three bonds to an oxygen, which is a good indicator that the oxidation state has increased. If you work it out, which we're not going to do, you can work out that the oxidation state has increased. But overall, this is what happens when we oxidize a primary alcohol. We form an aldehyde, and then we form a carboxylic acid, okay? And now, to undergo this reaction, we do need a specific kind of catalyst, which we would normally write here, above the arrow. We need either MnO4- Cr2O7 and we need these to be acidified, which basically means that we just have some H plus as well in the solution, and that allows the mechanism for this reaction to carry out, and we're going to produce our carboxylic acids and our aldehydes. Generally, we can just write that, for example, as KMnO4, so that we've bonded it to potassium, so that it's not an ion. But really, the important part is the MnO4. And we'll actually see how that's useful later on. To carry out this reaction, we also need the presence of heat. You can also write under the arrow. And those are the two main catalysts that we need to carry out an oxidation reaction. Now, you may be wondering, I mentioned there are three types of alcohols. There's primary, which we've seen overall goes to a carboxylic acid. But what happens if we oxidize a secondary alcohol, or as that matter, a tertiary alcohol? Let's take a look at that. Now that it's secondary, the hydroxyl group is going to be on this carbon, which is bonded to two other carbons. Now, for this, to increase the number of bonds that carbon has formed with oxygen, we want to have two bonds to oxygen. And again, that's going to be two bonds to an oxygen here. And then we'll have two on the side, where carbon's bonded to its two other adjacent carbons, and that's four bonds. So that's all we need. And if I draw out the full compound here, you can see that what we've actually formed is a ketone. So we've gone from butan-2-ol to butan-2-one. Actually, this would just be butanone. But if we had more than four carbons, we would need to specify where the oxygen is. Here, because ketones have oxygen in the middle, it can only be on the second carbon. And this is a one-step reaction. The ketone does not oxidize further because carbon has no more room to bond to oxygen. It's already got its four bonds made. So this is what we have. We're going to need those same catalysts. So acidified, potassium permanganate, and some heat. Now, for our final reaction, I'm actually going to change the hydrocarbon here, because to have a tertiary alcohol, have an alcohol like this. This would be, the longest chain is 4 carbons. On the second one we have methyl and hydroxyl. So this would be 2-methyl butan-2-ol. What happens if we try to oxidize this? Well, carbon's got 4 bonds, but we want to try and give it another bond to oxygen, right? Well, let's see. Could we maybe add 2 here? Oh, but then we've got 5 bonds, and we can't just get rid of one of these carbon groups. So in fact, you will find that we cannot oxidize a tertiary alcohol. Whereas before, if we had another hydrogen, we could take these electrons and put them into the double bond with oxygen. But now we don't have another hydrogen laying around, so we just cannot oxidize a tertiary alcohol. And this actually provides quite a useful test. So if we wanted to test between primary, secondary, and tertiary alcohols, then how could we carry out this test? Well, what we could do is we know that primary alcohols will oxidize very quickly, secondary alcohols oxidize slower, and tertiary alcohols do not oxidize at all. And one of our catalysts, MnO4-, as it undergoes this reaction, it changes from purple to colorless. I don't have a colorless texture, obviously, but so primary alcohols react quickly, secondary alcohols slowly, and tertiary alcohols do not react at all. And so to distinguish between these three, let's try to oxidize our unknown alcohol. If we see this color change occurring quickly, that means we have a primary alcohol. If it takes a lot more time, or if we have to add significantly more heat to push the reaction to completion, then that means we're going to have a secondary alcohol. And if no matter how much heat we add and no matter how long we wait, this color change does not occur, that means we have a tertiary alcohol. Okay, so that means if we look at our mind map here, we've covered adding halogens to alkenes and alkanes, we've covered the hydrogenation, and we've covered oxidation of alcohols. Another question you might want to ask, how do we produce alcohols at all? Well, we've already covered that. With a dilute acid, we can hydrate an alkene. But there's another way. If we take a glucose atom and we ferment this is my little mnemonic for the catalyst, then we can produce an alcohol. Okay, how do we ferment glucose? Well, glucose is a kind of complex structured molecule. If we look at a formula for glucose, what's going to happen is, as we add our catalysts, which I will discuss in a second, actually you wouldn't write zota, you would write zymase. For example, with this, we will form ethanol, which is C2H5OH, and we're going to form some carbon dioxide on the side. Okay? Now, we don't need to know too much about this reaction, only that we can take sugars and we can react them with zymase to form ethanol. Now, what are the actual catalysts? I alluded to some acronym earlier, ZOTA. This is how I remember it. Remember it however which way you like, but Z stands for zymase. This is a biological catalyst. It's a yeast enzyme that we need to put in for this reaction to occur. But there are certain conditions that this zymase requires. For example, it's very sensitive to temperature. So that means we need to have a warm temperature of around 30 to 40 degrees. Also, because this is a yeast enzyme, this can actually respire if we add oxygen. So we need to make sure we don't have oxygen. Conditions without oxygen are called anaerobic. And finally, this A just stands for the aqueous sugar, which we have here. This is what we can do with fermentation, and this is the final way that we have, apart from esters, which we don't need to talk about, to produce alcohols. Okay, now another method that I forgot to mention for producing an alcohol is by substitution of a haloalkane. So as you can see here in this diagram, if we have a haloalkane, for example, I've drawn 1-bromoethane, what we can do is react that with NaOH or some kind of strong base such as that, where we have a hydroxide attached to a metal, and then we will substitute and we'll swap out the OH and the halogen, much like with some other substitution reactions that we've been doing earlier. Then, of course, we'll see that we have the hydroxyl group now attached to the carbon where the halogen originally was, and we're going to produce sodium bromide or sodium iodide or whatever, depending on whatever halogen we originally had. For the reactivity of these haloalkanes, because more electronegative bonds are stronger, that means that Funkel-Brisk, the chlorine is going to be more electronegative, which means it will have a stronger bond to the carbon, and it will be harder to break that bond apart with your strong base. Bromide would be the next strongest, and then iodide would be the next strongest. So that means iodide would be the most reactive halogen for this method of substitution. Additionally, if we had primary, secondary, or tertiary haloalkanes, which isn't something we think about much, but it's the same kind of thing, where the halogen is attached to a carbon. How many carbons is that carbon attached to? 1, 2, or 3? What we'll find is that if we have more carbons attached to that one carbon, it's going to be more difficult to attack, and so we're going to have a higher reactivity when we have less carbons, i.e. a primary haloalkane, and then the reactivity decreases as we add more adjacent carbons. Now, this reaction isn't used very often because of its low yield. Often more in industry circumstances, we would be using something such as fermentation of glucose. And now the last reaction that we need to cover is neutralization. So neutralization traditionally occurs between an acid and a base to produce salt and water, or various other products depending on what kind of base or acid we have. Now, organic acids. Well, obviously this includes carboxylic acid, as the name might suggest. Whereas for organic bases, we have the amines. Now, amides, they have a lone pair on the nitrogen, so you might think they're a base. But actually with our amides, since we also have this oxygen, which is very electronegative, this is going to draw electron density away from the NH2 and up here. So that means that this NH2 group loses strength, and it's actually not going to have very basic properties at all. So for the purposes of this discussion, we can actually just ignore amides and just talk about the amines as our organic base. Okay, so first let's talk about... Okay, and now with our beautifully laid out information, let's discuss what happens with these organic acids and these organic bases. So we know traditionally with our acid reactions, there are three kinds of reactions that we can really have. If we have an acid plus a metal hydroxide, we create salt and water. If we have an acid with just a metal, we produce salt and hydrogen gas, and if we have an acid with a metal carbonate, we produce salt, carbon dioxide, and water, okay? And these three reactions basically are the same for our carboxylic acids. So if we have, for example, CH3COOH, you might know it as acetic acid. Technically it's ethanoic acid if we use the organic naming scheme. If we react this with a metal hydroxide, we're going to produce water and salt, okay? Water is a liquid, this salt would be soluble. What else? Still on the side of organic acids, if we react CH3COOH with just a metal, such as magnesium, we're going to produce magnesium acetate, which would be soluble, plus H2 gas. I forgot to mention that this would be in 2. Okay? And finally, if we react carboxylic acid, ethanoic acid, whatever, with metal carbonate, CO3, then first we've got H2O, and then we're going to have carbon dioxide, and then of course our salt. I believe this would be soluble, this would be a gas, and this would be a liquid. Okay, and the same thing, it's a bit messy, but if we react an acetic acid with a metal carbonate, we're going to produce water, carbon dioxide, and salt. Cool. So organic acids continue with the same reactions as normal acids pretty well. And if we look at the organic base of an amine, we're going to find pretty much the same thing as if we were to react the normal base of NH3 with an acid. This would go to NH4Cl. This is solid. And if I was to take, what's the simple organic base? C2H. And as we can see here, if we take a traditional organic base such as an amine and we react it with some acid, we're going to produce the corresponding salt, specifically an ammonium salt. And that's why we'll react with normal acids or with normal bases. But what if we react an organic acid and an organic base together? Well, that's where the interesting stuff happens. So if we were to take a carboxylic acid, amine, what are we going to get from that? Well, there's actually two possible reactions. If we have a low temperature, then we're just going to have a traditional reaction where the hydrogen swaps between, a traditional Bronsted-Lowry reaction, I should say, where the hydrogen proton goes from the acid to the amine, neutralizes them both, and we get a carboxylate ion plus ammonium. For example, here we've got ethanoic acid, and here we've got ethanamine, and if we react these together at a low temperature, this hydrogen will go to the lone pair on the nitrogen atom, and we're just going to get our generic carboxylate ion, which is the same thing as the carboxylic acid, but we've removed the hydrogen, and we're going to produce the ammonium ion here. So the hydrogen has gone over, now we have 3 hydrogens attached to the nitrogen, It's been neutralized. This is the conjugate acid, this is the conjugate base of that, and la-di-da-di-da, normal hydrogen moves, nothing interesting happening here. But if we carry this reaction out at high temperature, this is a really cool reaction. Now that we've given it a high temperature, we have enough energy to carry out a more substantial reaction. We're going to notice the H and the OH here. And we're actually going to take those to produce our water. And with what we have remaining, we're actually going to join these molecules together. This is really cool. So we have these two carbons, we have the oxygen, we now have a spare space here, and we're going to move this whole chain on. Okay, so I'm going to draw it in a different color, just so we can see exactly what's happening. So we still have one nitrogen and one hydrogen left, and then we're going to join the rest of the carbon chain on. That's not drawn super well, but it's okay. So now we've got the part of the carboxylic acid chain, and we've got part of the amine chain, okay? And this H2O is eliminated. This is really cool. I really like this. And because of what we got here, this is actually a secondary amide. So an amide, remember, we just have the chain, and carbon bonded to oxygen, and then nitrogen bonded to maybe another hydrogen. And this could be hydrogen, or it could be the rest of the chain. This could also be another chain, depending on what degree of amide we have. And since here we have chain, then carbon, oxygen, then we have nitrogen, H, and then here's the rest of our chain. So this is actually a secondary amide. I think this would be N-ethyl ethanamide. Crazy. And that finishes the final reaction that we really need to do here. Carboxylic acid turns into an amide as we add an amine under high temperature. Okay? That is all we have to know about our reactions. That may seem like a lot, but if you draw out your own flowchart like this, as I've done many times, it actually makes a lot of sense, and you can kind of see how everything connects together. And now to test between organic acids and organic bases, primarily carboxylic acids, or amines or amides, it's actually relatively simple. We don't really need to go through all this neutralization stuff. You can literally just get litmus paper and use that to test for the acidity of whatever solution we have. So if we have carboxylic acid or any other kind of organic acid, and we put blue litmus paper in that, that will be turned red by the acid. Similarly, if we have a base like amine, and we add red litmus paper to that, that is going to be turned blue by the base. If we have an amide, as I briefly said, those are really weak bases, so that's actually not going to change the color no matter what litmus paper we put in it. But basically we can just use that to test between if we have an organic acid or an organic base.
Now, don't you worry. I know just what you're thinking. I always do. These hydrocarbons, they sound interesting and all, but I learned by application. I want to get my hands on some of these juicy hydrocarbons. And how am I supposed to do that? Well, don't you worry. I have the solution for you. Fractional distillation. Now, what I actually mean is, how do we obtain hydrocarbons so that we can actually use all these properties in the world? What do we actually use them for? So we're going to get right into that, but first, a quick break from our sponsor, Brilliant.org. So basically, it's a 2 or 3 step process to obtain the hydrocarbons that we use. In general, step 1, we need to extract them from the ground, and then the next steps, we need to use fractional distillation to separate out the individual components of these to get, methane, ethane, butane, propane, and any other compounds that we need. Then, of course, we can use one of our reaction flowchart thingies like that to then go from having alkanes to having alcohols or ketones or whatever we need. Just a quick preamble. And fossil fuels are what happened when the fossils of these dinosaurs and other living creatures and organisms get compressed into the earth over millions of years by lots of pressure. And that just forms different types of coals that we find underground. And what we now want to do is extract these coals to form our hydrocarbons. Particularly, we have something known as crude oil, which is just a mixture of liquid hydrocarbons, and we have that contained underground as well. So how are we going to obtain this? You can see by my fancy-wancy-pantsy diagram that I've got here, which is where we surround the rock that we want to extract, which has our natural gas, which has all those hydrocarbons in it. We inject that with a lot of high-pressure water, sand, and some other chemicals. And what that does is that allows the rock to fracture, and the gas that we want flows out, as you can see happening here. And then we obtain that in, our containers and stuff. And we're going to then perform fractional distillation to separate out the individual components on this to what we actually want. Now, how are we actually going to separate out these different compounds? Well, you may remember that we spent a lot of time going through the different boiling points of these compounds, and how having stronger intermolecular forces, remember, gives it a
higher boiling point. That's just right. And we're actually going to exploit these properties, these physical properties, to separate out the different chemicals. So if we have something with a lower boiling point, that means we can add a smaller amount of heat and it's going to turn into a gas. Then we have this gas filter out through a tube, which we then collect. And then as we add more heat, we have compounds with higher boiling points being released, and then those come out. So as the molecules with a lower boiling point are being distilled out, we then grab those, and then we can go ship them off to our butane factory or whatever we're doing with them. This little procedure basically allows us to separate the different chemicals and then isolate them for our own usages. But now that we have these hydrocarbons, much like in Jurassic Park where the dinosaurs, you have to be careful with them, we have to be careful with these hydrocarbons too. They're not just safe little things like jelly or plant. We actually need to instigate some pretty strict but necessary safety precautions so that we don't kill people with these hydrocarbons. And now, saturated hydrocarbons, such as alkanes, are very good fuel sources, so we're going to use those in combustion a lot, because they release a lot of energy per molecule. Whereas the unsaturated hydrocarbons, such as alkenes, they're very reactive, and we can add halogens to them as we want. So they're more useful in things like electronics and medicine and toys, and anything that you've probably got around you probably has some kind of unsaturated hydrocarbon in it. Now, what is the actual impact on our planet of using these hydrocarbons? Well, I'm so glad you asked. So there's three main things we need to consider. There's the environmental aspects, there's the economic aspects, and there's the socio-cultural aspects. The environment is possibly the easiest one to consider the negative factors of. Okay, now, the combustion of saturated hydrocarbons, although it produces a lot of energy, it has some seriously negative environmental implications. Now, although combustion produces a lot of energy, it also produces a lot of carbon dioxide. Especially as we're using it to power our whole world, you can imagine that many molecules of carbon dioxide are going to be produced. And these go up into our atmosphere. Now, you probably already know what the problem with that is. It's that carbon dioxide is a greenhouse gas. It doesn't allow infrared radiation to escape the Earth, and thus it's going to trap our Earth in more heat, which causes sea levels to rise, which can cause more extreme weather events and disrupt natural wildlife. It is not a good thing. And we've seen the levels of global warming rising over the last 200 years due to the more carbon dioxide in the atmosphere because of this combustion. Even the extraction of crude oil that we were talking about before is actually quite environmentally damaging. Spills in this can lead to long-term damage to something called the water table. As well as that, with combustion of these fuels, sometimes we have impurities such as sulfur, which can produce sulfur dioxide, which eventually will acidify the oceans, which is going to obviously harm the sea life there, which require a very delicate balance of pH. However, on the plus side, I suppose, for our purposes with the environment, now that we can produce heaps of energy through this combustion of fuels, we can now start to develop the entire heavy industry. So that means we can make a lot more energy, and we can use that to mine more metals and minerals. However, of course, this is eventually just going to lead to more pollution. So overall, for the environment, we have a myriad of negative factors that we need to consider, mainly due to the combustion and what that does to our atmosphere and global warming. So it's mainly not a good thing for the environment. Let's talk about something more happy. Let's talk about the economy. We love the economy here. Now, the main things that we're using hydrocarbons for are producing energy and producing plastic through the polymers that we haven't talked about, but that's something that you can build with hydrocarbons. And because we can produce so much energy, it's actually quite a reliable source. We just need to, combust some hydrocarbons, then you got some energy. Combust some hydrocarbons, then you got some energy. And because of that reliable source, that means that we can now do a lot more long-haul transportation, such as through planes. We need a lot of energy to get planes from one side of the world to the other, and that's possible due to the combustion of fuels in hydrocarbons, which of course has positive implications for the economy. As well, the plastics that we have that are formed out of polymers, which are made from lots of little repeating hydrocarbons, have led to the production of many things, including computers, which we've all seen. I mean, maybe not people my age, but we've seen how much that has transformed the economy, and that has basically shifted our entire way of living, and that's definitely a positive implication. Because of polymers, we can also produce many advanced drugs and pharmaceuticals.
But of course, as we were talking about, because of global warming, that could actually lead to some negative implications. We could crash the economy if we don't stop burning up the world. In fact, there wouldn't really be any economy if we all die, which is quite possible due to all this combustion. So, some things you need to weigh up. I think overall, the positive implications for the economy seem to outweigh the negative implications, but we do need to be considering for the long term what's going to be happening if the world does crash due to global warming. Now, the last factor that we need to consider is the socio-cultural aspect of using hydrocarbons. So as I was saying, because we can produce many polymers with hydrocarbons, that means we can also produce many drugs and pharmaceuticals. And those are kind of medicine things that we can use to obviously drastically increase the quality of someone's life. I mean, there's so many things we can do with medicine. We can now even produce new organs for people to have that are made out of polymers. So that obviously is drastically increasing the quality of their lives. Many people are not dead, they are still alive due to the usage of polymers, which is a great thing that we need to be thankful for. Particularly because of plastics, we can now have disposable vials, which means we have much more sterile conditions that we're working with, and our medicine is much safer. Thus we can increase our efficiency, and everybody's quality of life increases. Big socio-cultural boom. Another thing that we might want to consider is that due to the ridiculous energy that is produced by combustion, again, it's always coming back to these main things, we now have a lot of electricity that we can power our houses with. And this means that we have efficient and cheap heating through the air conditioners that we have in our houses, and we have electricity that we can run off of and be productive virtually 24/7. So that may seem like a good thing, and I guess it is, we can be more productive, we can do more in the world because we can be awake longer, and we can do more with this electricity. However, this is also a bad thing from another way of looking at it. If we're being too productive, which is something that it's hard to stop now that we have this electricity that's powering us on or spurring us on, then this could lead to some stress and mental health issues, because we still need to have balance in our lives. We do need to have time when we're relaxing, when we're sleeping. We might not have that because of the increasingly reliable energy that causes us to just try to be productive 24/7. We also have some slowly rising evidence that increased exposure to hydrocarbons actually may have some seriously negative health impacts. So that will be a negative socio-cultural impact. Okay, cool. We've got ourselves some hydrocarbons, but now we actually have to work out how we're going to safely handle and dispose of these hydrocarbons. And that's what we're going to be discussing now. If we've got hydrocarbons out and about in our world, these are actually toxic to humans in high concentrations, which means they could be causing serious damage if things like soot get into our airways, or we accidentally drink a vial of butane or something, or if we have some kind of gas leakage. These could cause all kinds of health issues, so we're going to need to be working safely with these. Especially if we have short-chain hydrocarbons, those have less dispersion forces, thus they are easier to break apart the intermolecular bonds, or forces I suppose, and thus they're more likely to kind of explode if we put in just a little bit of energy, which means they're volatile. So if we're not storing these especially short hydrocarbons safely, then they could combust or explode. Even if we just have a leaky container of some butane, if that's getting into our atmosphere, that could be causing more combustion, and that could be causing serious damage to our airways. So first, how are we going to store and handle hydrocarbons safely so that these risks don't happen? We still need to keep our hydrocarbons around. They're one of the predominant fuel sources in the world. Just where are we going to keep them, and how are we going to keep them there safely? So often what we'll have hydrocarbons in these large metallic cylinders that have a lot of high pressure going into them. These need to be well maintained and fitting cylinders so that nothing is obviously going to escape, and so that it's not going to be damaged. You can often see these if you're like at a petrol station. There's all these big cylinders which are containing those hydrocarbon fuels. Even for things like petrol and diesel, we still need to make sure we have a really sturdy container for these. In this container, what we want to do is we want to store minimal quantities so that in case something bad does happen, it's only going to happen in a small amount. We want to keep it away from a naked flame to obviously prevent the chance of some kind of combustion due to the volatility of hydrocarbons. And we want to put a warning label on them so that people know what they're dealing with, and so that you can work out what's happening in case there is some kind of explosion. Another thing that people will sometimes do is they will add kind of smelly odor to these cylinders, so that if there is a slight leakage, we're going to smell that smelly odor much quicker than smelling the hydrocarbon, so that we're going to be able to detect if there is a leakage, and we're going to be able to stop it before something bad does happen. Okay, but how do we get the hydrocarbons there? How are we going to transport them? Well, often we're going to transport these in long kind of trucks with what looks like sort of metal cylinders in the back. Now what this actually is a reinforced steel container. So it's very strong like the metal cylinders, and it's going to be strong and well maintained so that we know there's no chance of the hydrocarbons escaping. These are often kept at the back of a truck or at the back of a car, and that's because the flame in the engine at the front, we don't want that to be getting near our fuel and combusting all of it, so we keep it at the back so it's safer. We also often add some colors to these chemicals depending on what kind of compound they are, so that we can identify these quickly and qualitatively in case we need to. Another thing that we have, particularly on trucks where we're transporting large amounts of these hydrocarbons, is what we'll have as a static electricity dissipation device. And this essentially, as we're offloading the hydrocarbons, to prevent, in case there's any buildup of charge on the truck or on the ground, which would create a spark and perhaps simulate an explosion of these hydrocarbons, because again they're so volatile, we want to dissipate that static electricity so that there's no chance of any kind of sparking occurring, so that we have safer opportunities for all. Now lastly, how are we going to correctly dispose of these chemicals? On each chemical, particularly if you're working in like a lab on these chemicals, I think required by law is something called an MSDS sheet, which will detail the correct handling and disposal procedures for you. As well as that, particularly for you chemistry students out there, as we're working in the lab, you should know you're never going to pour organic waste or hydrocarbons down the sink, because that could be very toxic for aquatic life. Instead, we have a particular organic waste disposal container. We also get those disposal agencies to collect our empty hydrocarbon containers. Okay, so cool, right? We've got all this energy from hydrocarbons and they've got some uses to modern society, but surely we could move past that with renewable energy. Surely we've got other ways to form plastic. Surely there's got to be some better option. Why do we still use hydrocarbons today? Well, that's a valid question, one that many scientists are still trying to answer, and still trying to find ways that, in some aspects, I suppose, with renewable energy, we can try and move on from hydrocarbons and use even nuclear power is better than hydro. Even nuclear power is better than burning and extracting crude oil and releasing toxic gases. But we're just so ingrained in our ways of using hydrocarbons. We've been using them for hundreds of years. They are probably the most efficient, they're release so much energy, and they're the most readily available. In addition to that, a large portion of the world still relies upon the power that these hydrocarbons can reliably generate. So it's not as if we can simply just cut away from them. Relatively, they're fairly easy to extract source of energy, they're much more efficient, and they're very cheap, okay? According to this source, we get 87% of our primary energy from things like oil, gas, and coal, which are contained in the fossil fuels that we discussed extraction of earlier. So that's 87% of the world's primary energy. That is a lot, and we currently do not have the power of renewable energy. We don't have that developed well enough yet to be able to switch away from hydrocarbons. Although, inevitably, if we switched away from them, the world would kind of just crash. This does make it difficult to transition away from fossil fuels. Although, inevitably, I suppose we're going to have to, because we only have about 50 years left of coal at the current extrapolations. So eventually we're going to have to run out and move to some other sources. But right now, that's really not a possible option, so hydrocarbons are still the best option for us today. Not to mention, as well as their insanely reliable and efficient energy, they're quite easy to transport, they create a lot of jobs, and they have countless uses in forming plastics and the halogenated compounds that we have in so much of what we have around us today. So clearly, hydrocarbons are still the best option for society today.